Should be. Anything?
Can you hear Stephen online?
Test.
Somebody tell us if you can hear Stephen.
Okay, thank you very much.
Thanks very much.
Okay, sorry, I'm just gonna take one more minute. There were lots of good questions that came up yesterday, and I want to address some of them. So we said this, and then there were lots of questions about smooth structures and other things. And I don't know if Kumar is here online today, but he specifically asked about like which polytopes or which sphere triangulations are polytopal. And I said something about it, but was forgetting some names. And I just wanted to say one more thing about this. Okay, maybe the first thing to say. So there's a very classical theorem due to Steinitz that says that first of all, every triangulation of a two-sphere is polytopal. So that just means it can be realized as the boundary complex of a convex simplicial polytope. So here, I think P is a simplicial polytope, but that's the same as putting a star here and saying that's a simple N polytope, as was our setup yesterday with Davis Januszkiewicz, who liked to work with simple things instead of simplicial things. And then above dimension 2, I suggested that there are actually a lot more sphere triangulations than there are polytopes. So here are some references. I said in words some result of Gil-Kalai, which is an older result, but there's some newer ones. These people tell us that, okay, let me take N at least 4 now. Then the number of simplicial n-1 spheres on our vertex set M is like big O, or I guess I should say big omega of 2 to the M times, I think, the 4 of n over 2. Yeah. So those are growing both with the number of vertices and the dimension quite quickly, whereas some other team of authors tell us that the number of like n polytopes thought of as, okay, let me say something in a moment. this is like exactly 2 to the big, what do we say, theta of m log m. Okay, so this result is counting things up to like combinatorial equivalence. So convex polytopes, just meaning convex hulls of points in Rn, but simplicial or otherwise. So really just like all polytopes, you only have this many asymptotically. And I think these results, since I said simplicial n-1 spheres on like m labeled vertices, these papers tend to count these things like up to equality on the nose. But notice that to count them up to isomorphism just means like you're counting unlabeled vertices. And that doesn't change the asymptotics because let's see, the like automorphism group of a simplicial complex K is at most m factorial, has size m factorial, right? If you've got m vertices, and m factorial is like big O of this, right? M factorial is less than m to the m, so you get this. So I don't think that changes this first bound here. So anyway, the point is,
Sorry, the second formula works with dependency on n.
yeah, that's the point, right? These ones do not grow with the dimension weirdly. Yeah, so as you go higher and higher in dimension, as soon as you're beyond like the range of Steinis's theorem, there's a bigger and bigger difference between polytopes and sphere triangulations. Yeah, it's really crazy how much the combinatorialists know about sphere triangulations. And there are even huge databases available where you can just see lists of simplicial sphere, like triangulations of low dimensional spheres up to 10 or 11 vertices. So of course, bajillions of these. And you can feed all that data into like Macaulay 2 or similar software, and you can compute the cohomology of the corresponding manifolds. We'll see why you can do that today. It can be boiled down to some like commutative algebra. So you can ask a computer to compute all these cohomology rings, for example. That can lead you to conjectures about what these corresponding manifolds must look like. And also someone pointed out the only examples that we really saw yesterday were of moment angle manifolds were like spheres and connected sums of sphere products. And this was maybe a bit misleading because these manifolds, you know, even if your K is just a sphere triangulation, so the homology of K, thought of as a space, has no torsion, the moment angle manifold can certainly have torsion. And the ring structure can also be like as complicated as you like. There's lots of results of Ivan Limanchenko and Buchstaber, which construct families of moment angle manifolds where you have Massey products, non-trivial Massey products of like arbitrarily high degree. So thought of as an A infinity algebra, the cohomology of these manifolds can be like arbitrarily complicated. The only ones that have been like identified in the sense of like, here's a manifold we know that has a name are like connected sums of sphere products. So beyond that, you can just pick some complicated sphere triangulation and you can compute that its cohomology ring is complicated, but you don't know what these manifolds are really. No one's identified any example other than things that can be seen to be diffeomorphic to like connected sums of sphere products.
Simplest one that has torsion is the triangulation of RP2.
Sure, yeah, that one won't give you a manifold, but yeah, the smallest moment angle complex with torsion might come from triangulating the smallest simplicial complex you know that has torsion.
I think they're constructing one for the manifold.
Definitely, yeah, you can have torsion and yeah, arbitrary torsion in the cohomology of a.
But the simplest moment angle complex, which has torsion in its cohomology, arises from the simplicial complex, which is the triangulation of RP2, the standard triangulation of RP2. And then Stephen pointed out that's not a manifold, but there are examples of manifolds which are moment angle complexes with torsion in their cohomology.
Yes, in the example you just gave, the example, the simplicial complex itself had torsion, which is RP2. So is there one where that one, if I rule out that, I want to look at simplicial complexes which don't have torsion and then have an example?
So
You know
we'll
what I'm
see
asking?
today, talk about the cohomology of polyhedral products, and then that'll eventually lead us to some big stable splitting theorems for polyhedral products. So we'll see today how the homology of K, the geometric realization of K, what that tells you about the homology of ZK. So yes, you can definitely arrange for ZK to have torsion by like taking K to have torsion, like Tony suggested taking a triangulation of RP2, for example. But even if your K has no torsion, like a sphere triangulation, you can still have torsion. In fact, there's a construction called like the Beer spheres, where you can take any simplicial complex at all, and you can do something with it to make a sphere triangulation, right? So you could take K to be a triangulation of RP2, I think, to be sure that there's torsion in there, and then you could take the Beer sphere associated to that. That's a sphere triangulation which would have that K sitting in there as like a subcomplex. And that torsion would then appear in the moment angle complex. Okay, so we can be more precise about these two things. There are lots of questions about this, so I just wanted to mention a result of Lee Tsai. We know exactly when the moment angle complex is a manifold, so it's not just for sphere triangulation. ZK is at least a topological manifold, if and only if K is what's called a generalized homology sphere. So that just means it looks like the triangulation of a homology sphere, right? So you might have like a fake sphere. It's the homology of a sphere, but it might have a non-trivial fundamental group. That would count. It really just means any sort of triangulation of a homology sphere where the link of every face has the homology of a sphere of the appropriate dimension. Or another way to say it is if the Stanley-Reisner ring associated to the simplicial complex is a Gorenstein ring, if you happen to know what that means.
One says that it's complete, that K is dual to a complete simplicial band.
Those are certainly examples of these, but about smooth, yeah, we can improve this second. This is like a big open problem now about smooth structures among all of these K. When this manifold have a smooth structure. Want to be really ambitious, we could ask how many. So beyond this, okay, maybe I won't write this down, but yeah, a result of, I think, Panov and Ustinovsky shows that if K is like the underlying, the simplicial complex underlying a complete simplicial fan, is that the way to say it? Or another word for this is like a star-shaped sphere triangulation. Those you can give a smooth structure in pretty much the same way that these are known to have a smooth structure. But beyond that, yeah, we don't know. It could be that all moment angle manifolds have smooth structures for all I know. Okay, so now on to today. Let me just recall our main definition. So K will still be official complex on the vertex set M. And the other bit of our setup, remember, was just that X underline A underline denotes some sequence of CW pairs. pointed CW pairs. And then definition, what this course is supposed to be all about was that first, for any subset sigma of our vertex set, we defined this to be a product. Eyes. So I'll keep writing this as a colimit, as a union. But notice that you could talk about polyhedral products in any category where you have products and finite colimits. And one interesting thing this gives you is a sort of functorial interpolation between products and colimits in your category. So I think this is roughly where we left off. So we looked at moment angle complexes to start, which were like each x and a just looked like d2 comma s1, but we could have started with something simpler. So let's consider the case when all of our a's are a point. Because in this case, you've got like the smallest simplicial complex being m discrete points. The biggest simplicial complex on this vertex set is a full m-1 simplex. In this case, x comma star to the k, or you might just write like x to the k, is just going to be a union or a colimit where you just have one space in your diagram for every face, but our only faces are vertices. So this is a union of m things, but each thing just looks like a point to like an xi somewhere. Just a bunch of other base points. So that's exactly the wedge of m spaces. And then at the other end, you had your product. So you should also maybe have like a zero object in your category if you want to do this elsewhere. But notice if you have products and finite colimits, then the limit or colimit over the empty diagram should give you like a terminal and initial object respectively. Okay, that's maybe a good first example. And then another one that came up in a few different ways yesterday was like take pairs like cx comma x. So let me just take m to be 2 here. So the reduced cone, some space, comma its base. Take k to be this guy, and discrete points. And our diagram is very simple, right? We've got like x1 cross x2, including into the cone, x2, right? This would be one piece of our union. Other piece of the union or colimit looks like this. So C everywhere here. It's the cone, and we collapse it by the base point as usual. So yeah, in that case, we saw that we get the join as a polyhedral product, right? You can also think of this as just the homotopy pushout of the projections to x1 and x2, since these cones are contractible, and that's maybe your preferred definition of the join.
That suspension, you can actually get that from polyhedral products.
Oh yeah, from the splitting, yeah. Yeah, I guess we'll maybe see it again and again. And there was one other thing about like this case right here of M points that I could have said yesterday about a moment angle complex, or yeah, notice that all these polyhedral products, these are literally subspaces. Next one. So djk always contains djk, remember, being this polyhedral product associated to the pair CP infinity comma base point. That always contains the wedge. So the first place where these two spaces differ, CP infinity just having cells in even degrees. I guess I really mean the first place djk and BTM, the first place where they differ can be in like dimension 4. So it's going to be an equivalence on 2 skeletons. And since there's no cells in dimension 3, it's actually an equivalence on 3 skeletons. So that implies that the fiber along that sequence of the vibration where the moment angle complex appears right here. Gives us that ZK is 2 connected. So I made a big deal at the very beginning of yesterday that moment angle complexes give us a big collection of finite, simply connected CW complexes where things like Moore's conjecture are interesting. So here's a good way to see why ZK is always simply connected. And then someone also yesterday essentially guessed that the like fundamental vibration from ZK to DJK to BTM can be hugely generalized by replacing the role of like S1 by any group. And then you could try to sort of generalize all of toric topology, replacing the role of a torus by like whatever group you like. And this is true. This is one good thing polyhedral products do for you. But I won't write that down yet. I think it'll come up tomorrow when we talk about some geometric group theory interacting with polyhedral products. So let me give those references later. And okay, some other examples. Polyhedral products related to things we've already seen come from like the combinatorics of subspace arrangements. So there's lots of objects one can associate to a simplicial complex, and a lot of them are very closely related to certain polyhedral products. So for any subset sigma of vertex set M, let me write L sub sigma for this subspace of C to the M. Defined by just like the vanishing of these coordinates. Sigma is the set I1 through IP, and let's just consider complex coordinate subspace. In the theory of subspace arrangements, people like to start with the simplicial complex and associate, do it a certain space called the complement coordinate subspace arrangement. Which is sometimes denoted just U of K, but it's just like Cm minus the union over all non-faces of K of these subspaces. So I just wanted to point out that this is exactly the polyhedral product like C comma C star to the K. So this is a good exercise to check that these two things are literally equal. And because the inclusion of like D2 comma S1 into this pair is of course a homotopy equivalence. The functoriality properties we briefly discussed yesterday, you would hope that would like induce an equivalence of polyhedral products. And indeed it does. So this can be seen to be an equivalence just because each of these is a co-limit of some diagrams, very simple diagrams consisting of like a K-shaped diagram of just products of spaces, right? And this map is giving you like an object-wise equivalence. So the co-limits are going to be equivalent. Okay, so that's maybe not so surprising, but even better, if you wanted to know that this like affine toric variety, okay, so maybe I should say this space here, instead of coming with like a TM action, comes with like a C star to the M action, making this an affine toric variety. And if you wanted to know that the moment angle complex is like a compactification, this affine toric variety, you'd want to know more than just this equivalence. And in fact, ZK is a TM equivariant retract. Is not such an obvious thing. Like it's tempting to just construct a map going from here to here in the other direction by thinking of like radial contraction or something. But it's not so easy to actually prove this. Okay, so these are like compactifications of these toric varieties in a sense. Notice that TM is acting on here just by restricting this action. And so if you're just interested in these spaces up to homotopy, then you can think of them as complements of coordinate subspace arrangements. And there's like a huge literature and history in this area of combinatorics where people study various subspace arrangements and try to relate the topology of their complements to like the combinatorics of the arrangement. Usually they're asking for the homotopy type of the complement of an arrangement is like too much to ask for. So a big theme there is to ask when is the complement of some subspace arrangement a formal space. So let me not write down a definition here, but formal spaces are just nice spaces where the cochain complexes are like quasi-isomorphic to their own cohomology. So they're roughly spaces whose cohomology are determining their homotopy type, at least rationally. So there's a lot of classical theorems in that area that say, okay, I won't write this down either, but a classical theorem of Brieskorn in the 70s just says that all the complements of any hyperplane arrangement are just always formal. So they don't have to be coordinate subspaces, but if all your subspaces are hyperplanes, complex hyperplanes, then the complement will always just be a formal space. So problem when ZK formal results of beginning with Baskakov and then later Denham and Suchu studied this in much more detail. Show that there are lots of K for which this thing has Massey products. So they're often not formal, but on the other hand, like I said, all the explicit cases that we know of where ZK, the homotopy type of ZK, can just be identified as like a wedge of spheres, products of spheres, connected sums of such things. Anything you build out of spheres like that are formal. On the one hand, everything that we can actually compute has been formal, roughly. But without identifying things explicitly, you can show that lots of moment angle complexes are going to have non-trivial Massey products, and Massey products obstruct formality. So this seems to be like a delicate problem, and there's been a lot of work on it.
Integral formality.
Sure, yeah, you could ask for much more than just rational formality. Yeah, a lot more has been done. Yeah, that's sort of a different notion. Okay, so hyperplane arrangements, I said, always are formal, but those don't really occur among these complements of coordinate subspace arrangements. So ZK is never going to look like one of those, except maybe in like some trivial situations. But a good start is to look at, okay, a hyperplane as complex codimension 1. You could think of complements of codimension 2 coordinate subspace arrangements. And it's not so hard to see that that happens by looking at this definition of L sigma up here, precisely when all your non-faces, showing up here, sigma naught and K, like all your minimal non-faces, just have size 2. So one of these things is looking like a complement of codimension 2 subspaces, if and only if K is just M discrete points. So that's maybe the first place to look after you know this. And theorem of Gurevich and Terrio says in that case that if this is a complement codimension 2, coordinate subspace arrangements or subspaces. Precisely when K is just discrete M points. And they identified the homotopy type there explicitly. I won't write out the formula with all the combinatorics of what spheres show up and things, but the point is you get a wedge of spheres, something of the homotopy type of a wedge of spheres. And then as you start moving away from M discrete points to like bigger and bigger simplicial complexes, this problem gets harder and harder. There's been a lot of work on this trying to just identify when ZK could have the simplest possible homotopy type it could, a wedge of spheres. Yeah, and with R and R star, that's still equivalent to the real moment angle complex. Okay, so that was just to indicate one connection, this area of subspace arrangements, and now I want to shift to cohomology, and to do that, we'll talk about some connections to commutative algebra. Specifically like combinatorial commutative algebra, or area known as Stanley-Reisner theory. So let me set some notation. Let's take S to be the polynomial ring on m variables, as many variables as we have vertices in our simplicial complex. I want to think of a generators as being in degree 2 so that I can identify this with a cohomology ring of the classifying space of a torus. K will usually be a field, but sometimes take the integers. Then first definition, can associate to K various rings, most important one being the Stanley-Reisner ring of K. So that's just denoted K, bracket K like this, and it's just a monomial ring. So quotient of S by an ideal generated by monomials. Where this defining ideal, called the Stanley-Reisner ideal, is just generated by all the monomials corresponding to non-faces of K. So like VI1 up to VIP, where the set of vertices I1 to IP is not in K. So as we said yesterday, a simplicial complex is determined to isomorphism by its minimal non-faces. And those minimal non-faces, notice, are just going to be the generators of this ideal. So for this example we looked at, I think it's two-face filled in here, labeled 1, 2, 3, 4. This Stanley-Reisner ring, K, would just be like polynomials, 4 variables, quotient out the ideal generated by like 1, 3, and 1, 4. Okay, and I think that makes it clear that every square-free monomial ideal is the Stanley-Reisner ideal of some K. So one can go back and forth between simplicial complexes and square-free monomial rings in this way. There's a whole area of combinatorial commutative algebra that studies like the interplay between these things, trying to import tools from combinatorics to study certain commutative rings and their modules, and vice versa, using like algebraic tools to study combinatorics. So algebra. So given some combinatorial input, usually it's simplicial complex K. They associate all these rings, so like the Stanley-Reisner ring, or let's call this Cazul homology, which is this Tor algebra. So this arrow is sort of like what combinatorial commutative algebra is all about, and toric topology gives us lifts where we assign to any K a bunch of spaces. Davis-Anaskevich space sort of sits right here. As a geometric realization of this ring, since that its cohomology is this ring. Turns out that the moment angle complex is this as its cohomology. And then there's lots and lots of other spaces. So if I took like the base loop space of DJ, its cohomology, or really I want to say it's like homology algebra, where the loop multiplication is giving you ring structure called the Pontryagin ring. That would give you, it's called the Oneida algebra of the Stanley-Reisner ring, which is X'd over the Stanley-Reisner ring. Or if I took the free loop space of this space, its cohomology would be like the Hochschild homology of the Stanley-Reisner ring. So in all of these cases, you can try to study properties of these rings by studying the topology or homotopy types of these spaces instead. Or you can take theorems from combinatorial commutative algebra. There are lots of them. And you can try to lift them to like topological statements instead. Okay, let me not write down the Hochschild homology one, but this is called the Zuhl homology. And this is called the Unite algebra. See this? And I'll just focus on these examples that we've started to see already. Okay, so let me like just sketch some proofs of both of these results here, but first recall that this arrow is going to mean that the Betti numbers of this space are the Betti numbers of KK. So if little k is a field in the dimension of these modules, graded modules, called the Betti numbers of K, or sorry, of the Stanley-Reisner ring, rather. Beta ij is like dimension over little k, 4. So we'd like to know how to compute these things. And
Tor groups are over which ring?
Tor is over S, where S is the polynomial ring. I'll call S this polynomial ring from now on. S for symmetric.
Just repeat that for them.
Oh, the question was, what is this Tor happening over? Thinking of both of these things as modules over our polynomial ring S. So the Stanley-Reisner ring is just by definition quotient of S, and the ground field is thought of as a module in the usual way. Yeah, I guess I could leave that there. So let's start with the Davis-Januszkiewicz space. It's sort of easy to see what the cohomology of a polyhedral product like that is. Remember, it's of the point of the form like x comma a point raised to the k. And there's lots of different ways of seeing that its cohomology ring is exactly the Stanley-Reisner ring. I think the easiest way to see it, though, is just to think of cochains. So you should probably attribute this to Davis and Januszkiewicz. Cohomology, djk, any coefficients, isomorphic as a ring, Stanley-Reisner ring of K. And the idea is just to look at like cellular cochains, say. So let di to k be the 2k dimensional cell, the ith coordinate or the ith factor. Cp infinity to the m, this m-fold product. Then like the cellular cochains. Of that product have a basis that just looks like, you know, take products of these cells to get a cell decomposition of the Cartesian product. So I want to write like di1 to k1 cross blah, 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 dip to kp. Star, right? Taking cochains. Yes, just the duals of these cells. And you've only got cells in even dimensions, so the cochain complex agrees with the cohomology. And then you can think of what this map does, djk including into this product, right? Inclusion, literal like CW complex inclusion is going to induce an injection on cells and a surjection on cochains, therefore. So let me be quick and just write that this is isomorphic for a polynomial ring, V1 to Vm. And this is corresponding to just like a monomial Vi1 to the K1, because remember, each Vi is degree 2. Okay, and then just observe. Snap on cochains induced by the inclusion. Is surjective with an obvious kernel. Right, the kernel will just be like generated by all of these basis elements where I1 to IP is not a cell that's present in this subspace of the product. Yeah, I guess I should write it like this. Right, I1 to IP not contained in K. So that's roughly all you have to do to see this isomorphism. And the proof also shows that like the map induced by this inclusion djk going into DTM, right, the product of CP infinities, induces in cohomology what you would hope, namely just the quotient map from our polynomial ring to the Stanley-Reisner ring. And then this whole like fibration, set k to djk to DTM. Is analogous to, okay, in algebra, S is mapping this way, to some S mod I. Here I should write Stanley Reisner ideal S mod IK. So just algebraically, if you consider this quotient map, there's something called the derived fiber of a homomorphism of rings. It's usually talked about in the context of like local rings, but it works for graded rings as well. Derived fiber usually be written like this. So that's just some object in the derived category of derived category of S modules. It's just a DGA that computes Tor. And we'll be able to be very explicit about this DG algebra soon and actually compute things. But given that, this second theorem shouldn't be so surprising, right? That the cohomology of ZK is exactly this Tor sitting in a fibration like this. It looks like it should induce this sort of exact sequence algebraically. Okay, so how does that theorem go? This one is due to Björkstrauber-Panov. And also Matthias Franz. So K here could again be any field or the integers, and this is this Tor algebra. Calling it a Tor algebra, we should maybe review some basic homological algebra, why this thing has a ring structure. So how to compute? There are at least two good ways. One is using something called the Kazul resolution, or the Kazul complex. Another classical way from commutative algebra is something called Hochster's formula. It's just some celebrated result that is right at the beginning of combinatorial commutative algebra that describes the Betti numbers of a monomial ring in terms of like the combinatorics of K. So we'll see what that is in a moment, but it's something that works for just any monomial ring, because if you have any monomial ideal, something called polarization, which will take your monomials to square free ones. And this polarization process doesn't change Betti numbers. So one can always reduce to square free monomial rings, and those are all of the form K of K for some simplicial complex. So it gives you a very powerful like combinatorial way to study Betti numbers and generality. Okay, so for approach one, let's just quickly review some homological algebra. If M is like a graded S module, I want to say finitely generated, graded S module. So Si tensor Mj is mapping to Mi plus j. And what is a free resolution in this graded context? We all know, but I just want to emphasize that it's really like a bigraded complex of free S modules. And this bigrading is going to be kind of important just because like the ith homological degree of Tor here isn't going to correspond to like the ith cohomology group exactly. There's going to be some shifting going on involving the bigrading. So then a free resolution is just something like this. I'll write complex F D that's quasi-isomorphic to M or S module equipped with the zero differential. And I'll use this negative grading, so like F minus I, it's right here. Differentials continuing on. Got F minus 1, going to F0, and then to 0. Quasi-isomorphism is happening right here. So each of these objects, of course, individually is graded module over S. And like horizontally, I'm just having zeros out here. So yeah, F altogether is like I-graded thing, Ij, F, I'm writing minus I, J. I guess a bi-graded free S module. F minus Ij just means like the jth component of F minus I right here. So J, think of as like happening in the vertical direction. And we'll call this the homological degree as usual. And the J is like some internal degree. Okay, so how to resolve one of the two arguments in our Tor over there? We're supposed to, resolve this and then tensor with this over S. That'll break exactness in this thing somehow. And then homology there. It's computing Tor. Or conversely, we could resolve this and then tensor with this over S. So resolutions of Stanley-Rice rings are quite complicated. That's why people are interested in like the Betti numbers of these kinds of rings. But there's a very nice resolution of just the ground field K we can always use. So maybe I wanted to say over here, do the three sphere? Where's a sphere? Oh yeah, sure. We'll definitely do an example. I don't know if there's much to do in that example, but so I guess I'm writing minus I J here. And N H minus I, like that. F tensored with N. Okay. Okay, so this is where the Cazul resolution comes in. We're going to consider little k as an S module in the usual way. Give this augmentation map I'll call sigma. So you know all the variables go to 0 and 1 goes to 1. And then let's set F to be the tensor product, just an exterior algebra on M generators. Tensor is over the ground field here. Our polynomial ring on these V generators. I said this is supposed to be a bi-graded free S module. Okay, it's free just by construction, some vector space tensor S. And I'll give the U's by degree -1, 2. And the V's, which are the generators of S, will have by degree 0, 2. So total degree 1 and 2. The differential will just send degree 1 guys, these degree 2 guys. So set like d of ui to be vi for all I, and then just extend by like the graded Leibniz rule to get a differential. Then what I'm saying is f comma d mapping to just the ground field equipped with a 0 differential is a free resolution called the Cazul resolution. So the like exterior powers or the number of u's you see in a word is telling you the homological degree. So you'd have like lambda m over here, u1 to um, answer s. And then this differential, is always going to turn a u into a v, right? So you're going to lose 1 u at each step. It's going to go all the way down to like lambda 0. Say lambda 1, I guess. And lambda 0 is just the ground field, so that's just our s. And from s, I can do my augmentation, epsilon to little k, and that's going to be the quasi-isomorphism. So this is called the Cazul resolution of K. Don't need this. Okay, so reviewing that was supposed to just, allow us to both compute some examples, but it also shows us a way just to prove this by thinking of the cochain level of both sides. This is a CW complex. We can maybe think of its cellular cochains in a straightforward way, and we now have a cochain complex underlying this side. And we could maybe just be very explicit and construct a map that realizes this isomorphism. So yeah, let's take a break there. We'll do an example and then get to these stable splittings. Yes, please.
Would anybody like to go, please?
In the equation there, where is the J independent on the right-hand side?
Sorry, independence on the right-hand side?
J dependent.